we are going to calculate the effect of adding a small amount, 0.20 moles, of a strong base to a buffer solution. This is a buffer solution. We see that there's high and relatively equal concentrations of a weak acid and its conjugate base. The acid part of the buffer is the acetic acid, COOH. So we can see how it reacts with the hydroxide. This is a 100% reaction. Strong acids and strong bases react completely. So the base is going to accept an H plus and produce water. And the acid is going to give up its acidic proton to form its conjugate base. Essentially what has happened here is the strong base has been converted to a weak base, and therefore there's going to be little impact on the pH of the solution. So as we see here, the concentration of the acid part of the base is going to decrease a little bit, and the concentration of the base part of the buffer is going to increase by the same amount. Now we're going to consider the quantitative aspect. This is a buffer, so we're going to use the Henderson-Hasselbalch equation. We know the initial concentrations of the conjugate acid-base pair, but we don't know the concentrations after the hydroxide has been absorbed. Here we've calculated the initial moles of our weak acid and the conjugate base. We know they're equal because we have equal concentrations and they're in the same solution. So if we multiply the molarity times the volume expressed in liters, we'll get the moles. So we have 0.50 moles of HA and the same amount of its conjugate base. I'm going to use a BCA table to keep track of things. BCA tables are very similar to ICE tables, only we're dealing with quantities in terms of moles. We've calculated that we initially have 0.5 moles of both the weak acid and its conjugate base. We've added 0.02 moles of our strong base. So these are the amounts that exist prior to the strong base reacting with the buffer. When the strong base reacts with the buffer, it's going to be completely consumed, and we lose that amount of our weak acid. So now we have 0.48 moles of our weak acid, and we're going to gain an equal amount of that weak base. So we have 0.50 moles of our weak base. And of course, all of our strong base has been absorbed. We're going to save ourselves some time in calculations. We remember that our weak acid and its conjugate base are both in the same beaker. So the ratio of moles of the base to moles of the acid is the same as the concentration of the base to that of the acid. So we do not need to do a separate calculation where we determine the actual concentration of the base and the acid. Here they're just in 1 liter, so it's easy, but there will be other situations where it is not. Keep this in mind. It's going to save you time in a lot of problems. Because these substances are both in the same solution, the ratio of their moles is the same as the ratio of their concentrations. Here we've set up our Henderson-Hasselbalch equation. We've found our Ka, so we're going to calculate our pKa, and as far as our new concentration ratio, we have the moles of our base, A minus, divided by the moles of our acid. we've chunked out our numbers, and we have that the pH after the added hydroxide is going to be 4.7795. To our same 2 sig figs, we have a value of 4.78. Now our initial pH of the balanced buffer was equal to its pKa value, which in this case was 4.74. So we've gone from a pH of 4.74 to a pH of 4.78. So our delta pH is only 0.04 units. The buffer minimized the impact on pH of adding this amount of a strong base by absorbing it and essentially converting the strong base to the weak base that's found in the buffer.